First of all, if you can't hear me, please just raise your hand and ask me to speak louder. I would like to begin by thanking John, Visha, and the organizing team for this workshop. As some of you know, or as some of you will find out, organizing something like this takes a lot of effort. So I hope you join me in thanking these people. So thanks. And also thank you for being here. Let's proceed straight to it. So John really nicely started the talk by saying that this research component is the cutting edge of, it'll present some of the results of the cutting edge of PN. And I'm convinced that the results here that you'll see are the cutting edge, but maybe 10 years ago. Okay, so let's start with the motivation. And this is about Bayesian inverse problems, which in particular for initial value problems, which are very common in a lot of scientific applications. So you've seen a lot of this stuff already, but let me just formalize everything. So we have an observation model, which takes the form as what you know, the data Y is the noisy, a noise-corrupted image of some true parameter, x star, which is fixed, under some so-called parameter to observable map or forward model G. So x star is the truth and epsilon is the noise. And the inverse problem is given the data Y, we want to infer the truth x star. And this is typically very difficult, and this is one reason why people like inverse problems, because first of all, they're ubiquitous. Second of all, they're really challenging. So typically, G is a many-to-one. It's a non-injective map. So even if you have no noise whatsoever, just knowing G of x star would not enable you to retrieve x star from. Okay, the Bayesian approach, again, as you are now all experts, or were already experts, is we want to model x star, which we don't know, using a random variable. So this is like probability or stochastic modeling, the very first course, right? We don't know the outcome of a coin toss, so let's model it using a Bernoulli random variable. And we do exactly the same thing here. Since it's a random variable x, it has a prior law, which I'll denote by mu pri. And we choose a likelihood, L of x and y. And this is essentially determined by your statistical model of the noise, or your probabilistic model of the noise epsilon here. Once you've chosen a distribution for epsilon, in this case normal, with mean 0 and covariance C, that's positive definite, you get immediately a likelihood. We then solve the inverse problem. So for the Bayesian, the solution of the inverse problem is not a fixed point, a deterministic estimate of x star given y. It's a probability distribution. And it's the posterior which you obtain by integrating the likelihood against the prior. Okay, so now let's specify, narrow down our inverse problem to the setting of initial value problems on some fixed time interval 0 to t. And we assume everything that we need to assume such that this initial value problem has a unique solution z, which depends on my unknown parameter x. Okay, so, and it's formulated as a differential equation, which you're all familiar with in the finite dimensional setting. So the time derivative of z as a function of t for fixed x is given by a vector field f, which takes in your state at time t, but can also depend on the parameter x, and your initial condition can also depend on x. Okay, so from this initial value problem, we can construct a solution operator S. And what it does is that it's a mapping from your set of parameters calligraphic x to the set of all continuous trajectories from 0t to, say, a Hilbert space H. And you could think of H as just being Rd. So what this map does is that S takes every parameter x in your space calligraphic x to a trajectory, a continuous function z for fixed x. So this is not enough. I mean, we've heard of multiple talks here where we have an information operator. And for this to kind of connect these two ideas, we're going to define an observation operator O. What O does is that it says, give me a trajectory in a Hilbert space, and I'll give you a vector of snapshots of this. So think of it as a movie, and you just take snapshots of the movie at fixed times t1 and tj. Okay? So now O of z, where z is a trajectory, is now a vector in j copies of h. The parameter to observable map now is a composition. It's just take the solution operator, feed the output of that into your observation operator, and now you have a vector in h to the j. The problem is that in many cases, we just heard a really nice talk from Moto about model misspecification. There was also a talk yesterday about this. We don't have the true solution map. Even if we assume that our PD or ODE is the correct representation of reality, which in general it's not, we can't even solve that exactly, right? So we don't have access to S. So, and in particular, this means that even if we knew the observation operator exactly, we could not get G. We can't actually use G. So again, let's go back to the example of a parameterized IDP. We can't solve this ODE exactly. So we resort to an approximate solution map, S subscript H, which does exactly the same thing, except that it depends on a resolution or a mesh grid or a time step, which I'll denote by H. And this is always going to be positive. We would like it to be 0, because that would kind of say we have access to the true solution map, but we never do. So the resulting approximate objects are exactly as you would expect, right? We feed the approximate solution operator SH, we pass it to the observation operator, this gives us an approximate forward model GH, and we can then put GH to our likelihood, combine it with our noise model to get the likelihood, and now we get an approximate posterior, mu y pos h, which depends on our resolution parameter h. And the natural questions are, how do we account for error in our approximate forward model? And second, how does the error in the approximate forward model then propagate to the error in our posterior? Typically, we're never going to stop with just the posterior. We want to use the posterior for something downstream, or it's in a computational pipeline, which you then use to make decisions, like we saw in Mark's talk yesterday. This leads us to the next part of the talk, which is about numerical methods and statistical inference. We've seen a lot of nice examples in the school and in Moto's talk about overconfidence or underconfidence. I will just talk about overconfidence here. And this kind of relates to the question of, or it's connected to the question of, how do we account for error in the approximate forward model? So the answer of Conrad et al., which is, for me, really how I got into PN, and it's an old paper, but it's a really nice paper, is to use random variables, right? So there's this foundational model. If you don't know what the outcome of a coin toss or a random experiment is, model it using a random variable. And so here's the parameterized IVP that we had before. Suppose we have a deterministic time integrator, and that's denoted by psi. So psi is just a mapping from a Hilbert space to the Hilbert space, and we assign it some time step or a mesh resolution h. Okay? And what it does is that you give me the current state at time kh of my approximate solution, and feed it into this deterministic time integrator, and then I get out of that the state of the solution or the trajectory at the next time step. I then define the approximate solution operator SH just by doing linear interpolation between these points or these snapshots. Okay? This, what Conrad et al. Proposed, and at the time was, I would say, as the people who know here, is a really controversial idea. I mean, I think they received a lot of resistance from classical numerical analysts, because why would you take a perfectly fine deterministic method and mess it up by randomizing it? But this is what Conrad et al. Did. So they said, let's do the same thing, but every time we apply the deterministic time integration step, let's add random noise. Why do we do this? We saw from Philip's talk yesterday is that when you solve an ODE, you're integrating. But we can't evaluate integrals exactly. There's always going to be some truncation error. We can say, okay, we choose a really small time step, and we say that the vector field is constant over this time interval. That induces an error, a local truncation error, which we don't know. If we knew it, then we would solve all our ODEs and PDEs exactly. But since we don't know it, let's model it using a random variable, psi k, k for the discrete time k, and h for the time step, and omega to emphasize that it's a random quantity. This random quantity models the thing that we don't know, the error in our deterministic time integrator. Okay, and now that we have a way of solving, or creating a random solution, approximate solution of the ODE, we can now construct a random solution operator S hat, which takes in a parameter value x, and depends also on your randomization omega. We just do linear interpolation again. So here's an example of a Fitzhugh-Nagumo initial value problem. It's a two-dimensional ODE, and it depends on 3 parameters, so theta 1, theta 2, theta 3 in the ODE system that you see here. The solution map takes this parameter vector theta and spits out a trajectory in, from 0t to R2. Let's choose that as a deterministic integrator implicit Euler because it's nice, it's stable, blah, 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 blah. And this results in an approximate solution operator SH. The randomized integrator does exactly the same, except that, as you know, we add a random variable at each time step. And this yields a random approximate solution operator S hat subscript h. So I'm going to denote by nu h the joint law of all of these random variables that I add over the course of my solution. So what does this look like? Here's an example. At the top part, you see basically the black line is what you would say is the deterministic solution. This is our reference solution. And you basically see a cloud of red dots. So these red dots are the states of a randomized solution at the discrete times. And the blue dotted, that's like the mean, the ensemble mean. So you have an ensemble of trajectories. And they have a mean, as you would expect. And you hope that their spread of this ensemble is sufficiently large that it will capture the true solution. The bottom panel just shows you what happens if you kind of smooth this out and look at standard deviation intervals, for example. Okay. Why is this relevant? Well, because randomization can be used to tackle overconfidence, as we have seen. What you see is a plot of basically of a contour density. We place a probability density on the parameters just theta 2 and theta 3, okay, so that we can visualize things. And on the left-hand side, on the left column, you basically see the results if we don't do randomization at all. And what you see is that at time step 0.05, so that's the blue line, the contours of this density are really concentrated, as you would expect. And they're not exactly at the truth, which is where the dashed lines intersect. As you refine the time step, let it go to 0, these estimates get better and better. But they're still very confident, and they're still wrong. If you do randomization, you introduce a lot of noise, and this basically forces your contours to spread out. It's a way of capturing the uncertainty that we have about the solution because we don't know the errors every time we apply the deterministic integrator. And as you would expect, as we refine the time step, so at really coarse time steps, the contours are really spread out. And as we reduce the time step to yellow, to green, and to red, the contours start concentrating. They're not completely collapsed, but they get a lot more concentrated. And they are sufficiently wide such that they cover the true value. So this is nice, okay? And I should warn you, those are the last two images you'll see in this presentation. I don't have the courage to do live coding because the last thing I did was say hello world. Okay. But the nice thing about this is that you can actually do overconfidence in an analytical example, a really simple system. And this example is really based on an idea of Asir Abdullah and Giacomo Garignani. Let's look at a linear Gaussian Bayesian inverse problem. It's in fact just inferring the initial condition from a heat equation. So this is now posed on a Hilbert space, which you can do. You have a self-adjoint linear positive operator A, and you formulate a differential equation on Hilbert space. The linear forward model is simple. It just says, starting from your initial condition, evolve forward for time h, which is small, right? As you all know, inferring the initial condition from a heat equation is an ill-posed inverse problem. It just doesn't work. So let's do it in a Bayesian way. We want to infer the true parameter, which is the initial condition, from the data, which is just like an observation of the state of the system at time h. This is now where we get to see something that we've seen again and again these past 2 days. If we assume a Gaussian prior, because this forward model is linear, the posterior is also Gaussian. And you know, in fact, exactly what the mean is and what the covariance is. So what we see is that the posterior mean is the prior mean plus complicated stuff from the Gaussian conditioning formula, which involves the forward model, and now the observation noise scaled by sigma. I should mention here that I'm taking epsilon is normally distributed mean 0, covariance is gamma obs, and I scale it by sigma. And why I do that will be clear in a moment. Okay, and the covariance, as you all know, it doesn't depend on the data, but it depends on everything else. So now we're going to study the small noise limit. In Motonobu's talk, he looked at the large data limit as n went to infinity. That's one of the classical limits in statistics, as you know. And another classical limit in statistics is what happens when the noise in your observations goes to 0, right? If a statistical inference procedure doesn't work well when there's no noise, you probably shouldn't use it, right? So this is one reason why this limit is studied. Right, is that me? No, okay. So the behavior in the small noise limit as sigma goes to 0 has this following effect. The covariance operator shrinks to 0. So this is the vanishing variance. It indicates that the posterior variance goes to 0 as the noise limit goes to 0. On the other hand, the posterior mean actually contracts or converges to the true parameter x star. So the bias vanishes. The bias in your posterior mean vanishes. Because we're Gaussian, the mean and the covariance determine everything about the measure, the posterior measure. And because of these things, you can actually show that the posterior converges weakly in the small noise limit to the Dirac delta at the truth. And this is really what you would like because it indicates that the statistical inference procedure is consistent in the small noise limit. What about the approximate posterior? Remember, this is what we had when we don't have access to the true solution operator, but we approximate it using some finite mesh or finite resolution numerical method. We do everything as we do before. We use implicit Euler, and we get an approximate forward model G tilde H. This is deterministic, and implicit Euler just has this form, right? It says, give me your state, and I'll tell you my approximation to the evolution, which is basically like a first-order approximation of the exponential. We use the same data in the prior as before. The approximate posterior is exactly what you saw from the previous slide, except that I replaced G with G tilde H. Now what happens in the small noise limit? The covariance goes to 0, so we have vanishing variance. But the posterior mean for fixed H, in the limit as sigma goes to 0, it converges to this quantity, which, by working with the definitions of G tilde H and of G, just give you this, right? And as you know, that's not exactly equal to X star. So we have non-vanishing bias in the small noise limit, but our covariance is shrinking to 0. And this is an example where we have overconfidence, right? Because now your posterior is not going to converge weakly to the Dirac at X star. So we have an inconsistent statistical inference procedure when we are using the approximate posterior. So some observations. We have overconfidence in the small noise limit because we have vanishing variance, but non-vanishing bias. The bias is related, as you would expect, it's related to the error of our approximate forward model G tilde H. And in fact, you can bound the bias by an operator norm of G tilde H minus G, which is, heuristically speaking, like the worst case error of one H step of implicit Euler. So Conrad et al., as we know, they used randomization to account for the unknown error. And then we can ask, okay, how does this affect the posterior now? If we do the whole thing and we start with the same initial value problem and we randomize implicit Euler. So now we're working with a random forward model, G hat H, whereby we've just added one random noise scaled by H to the P plus 1. We use the same data in prime. And remember that we're using this random variable to model this error that we don't know. The approximate posterior, if you crank the whole Gaussian formula method, it gives you the following. The approximate posterior, mu hat, depending on your fixed time step H, is Gaussian with mean M hat H and covariance C hat H. It turns out that since our noise has mean 0, the posterior mean M hat H is the same as the thing that we had before. The covariance, on the other hand, is different. So now you have this additional term, H to the 2p plus 2 times gamma 1, which is the covariance operator of zeta. And why is this nice? It's because it counteracts confidence. For a fixed H, as you do the small noise limit, what's going to happen heuristically is that, well, this term is going to go to 0, but this term is going to remain. And because this term remains, this limiting covariance operator is not 0. So you don't have vanishing covariance. So this is an analytical example which shows you randomization can be used to counteract overconfidence, as you all know by now. Okay, so we have a true posterior associated with a true forward model G, and we now have a random approximate posterior that we want to use to counteract overconfidence. The natural question is, how does the error in our random approximate posterior propagate, in the random approximate forward model, G hat H, how does it propagate to the posterior? And some work with Tim Sullivan and Aretha Teckentrup from 6 years ago now says that under some technical conditions, you can actually bound the Hellingen distance in mean square between the true posterior and your random approximate posterior up to some constant, which is complicated and in general impossible to evaluate, times a double expectation of the error between your true forward model G and your random approximate model G hat H. And this is one instance of showing local Lipschitz stability of your posterior as a function of your forward model. This builds on foundational work by Andrew Stewart from 2010, and was continued 10 years later by Björn Sprung, who took a nice approach as well. And you can prove a similar result if you don't like the Hellinger distance, you can work with Kullback-Leibler, for example. So this is the inequality that we had before. It's a nice way of saying if you can control the error in your random forward model, then you automatically get, under conditions, control of your random approximate posterior. And the Hellinger is nice because if you're interested in square integrable quantities of interest that you push your posterior to, you automatically get control over such functionals as well. So now the question is, how do we control the right-hand side? Right? That's what we would like to do, such that we can control the error in the distributions. Recall that we had this time integration of the initial value problem. We have J state observations at time t1 all the way up to tj. And we have these forward models. We can actually, because we're using the same observation operator for both G and G hat H, we can control the error in the forward model as the worst case of the error in this trajectories. So the rest of the talk is about bounding the omega expectation of this. Okay. Are there any questions? Yes? Omega is just, it's like the randomness variable. It's to emphasize that this quantity here is a random variable. It's my discrete time solution at time tk with time resolution h, given that I've randomized at every step with random variables that depend on omega. So for every instance of omega, this will be something different. Thanks. Okay. No. All right. So this is, finally we get to the topic of this talk. Yes? Sure.
Just a quick question. So the idea going forward now is if I can actually bound the arrow in the forward model, minus the approximate forward model, I can use that as a noise scale for the noise that I inject. Is that the...
That's a good question. I won't go that far, but I'll try and address that issue later. Yeah, that's a good question. Thanks. So, Conrad et al. This paper, if any of you have read it, it deals with ODEs and finite dimensions. And a natural question to ask is, how does this extend if we're looking at PDEs? So John mentioned in his nice talk that PDEs, and as you all know, PDEs are ubiquitous everywhere, especially time-dependent ones. And it would be interesting to see, can this idea, which is kind of simple, does it work when we look at PDEs? So now I have to introduce some notation. It's a little bit ugly, but bear with me. We have an exact flow map. This is what we saw in Philip's talk as well yesterday. It maps a time, t, and a state, us, to a next time, t plus h. So I move time forward by h, and I also map forward the state by time h. So that's all the flow map does. It just says, where are you at what time, and I'll tell you where you are next time, in some whatever time h in the future. And it's just integrating along a vector field. That's all it does. Let's fix a time grid on the time interval 0 to t with some possibly irregular spacings hk. And I'm going to define h to be the maximum time step. So as h goes to 0, all of the time steps are going to go to 0. If I apply this flow map to this time grid, I get a deterministic exact solution sequence, z at tk plus 1. So z here, without a subscript h, is the true solution at a certain time. If I apply an exact flow map, psi, like implicit Euler, and randomize, I then get z hat subscript h, which is like what we saw before. The only difference is that now I'm not saying is my Hilbert space finite dimensional or not. Okay. So just to recap, what did Conrad et al. Do? They said, let's fix a uniform time grid, so all the time steps are the same. We assume that the vector field is globally Lipschitz, which is quite strong. Many ODEs of interest are not globally Lipschitz, but this is like the first paper, so it's convenient to start with strong enough assumptions. And because of this, your flow map, your true flow map, is globally Lipschitz as well. They assume that the randomization in L2 norm decays like up to a constant, which I'm hiding here, by h to the p plus 1 half. And they assume that their deterministic time integrator had some order q, and some maximal time step h star, such that if you use a sufficiently small time step, then you could basically bound, in worst case, the error of your deterministic time integrator, psi, relative to your true flow map, phi. And the order of that is h to the q plus 1. So this is a uniform local truncation error assumption on their deterministic time integrator. It's valid if f is smooth enough and has bounded derivatives, which in general is not true. Okay, so under these assumptions, they showed that if you start your randomized deterministic integrator at the same initial condition as your as the true solution, then you can actually bound the L2 norm at any point, tk, up to h to the smaller of p and q. So this is like one of the really nice bounds in their result, because it says that q is the order of my deterministic integrator, or my numerical method, and p is the order of my randomization. This bound says that if my noise decreases too fast, what will dominate the error, the worst case error, is the order of my numerical integrator. Conversely, if my noise decays to 0 too slowly, then that's basically going to take over. Okay. So this bound tells you that you don't want to, your randomization should be, in a sense, calibrated to the numerical method that you use, such that it provides a reasonably good model of your truncation error. So what we did is that we said, okay, let's try and port this to the case of where your differential equation is now on a Hilbert space. So this allows you to look at time-dependent PDEs, for example. we're going to kind of avoid placing any assumptions on our PDE by just assuming that there exists a unique solution of our PDE that's a continuous trajectory that takes values in a Hilbert space, like a Sombra space. But now we put a whole bunch of assumptions on our deterministic numerical method psi. We assume that it has an order Q, and we assume that it has a truncation error function, which depends on our flow map because it's a truncation error. That's bounded on bounded subsets. This is not such a strong assumption. This next assumption is kind of weird when I first encountered it, but I assure you I didn't come up with it myself. It's from a book on time integration for PDEs, which indicates that this is something that the people who work in this area are fine with. Okay? So we assume that there exists a dense subset, calligraphic D, of our Hilbert space, such that for any time and state that lies on a trajectory, where the trajectory started somewhere in this dense subset D, I have a truncation error of this form. I can bound the Hilbert space norm of the difference between the true flow map started at time t and x and propagated forward time h, and the deterministic numerical method, which is applied to the same inputs. I can bound it by this function, which is bounded on bounded subsets, times the time step h to the power q plus 1. And then I also assume that my deterministic numerical method is Lipschitz continuous. So the first condition is basically a non-uniform local truncation error of my numerical method. And the second is a global Lipschitz continuity argument for this, just with respect to space. What about the randomness? So given something called a Young function, which is something convex and starts at 0, it's defined only on the non-negative reals. I can define in something called an Orlich norm. And the Orlich norm is defined here. So for some function upsilon, the upsilon norm of a random variable w is defined in this way. This definition is not really important for what goes forward, but you can actually show that it includes as special cases any LR norm which is for r strictly larger than 1. Even nicer, if I choose the Young function to be exponential of z squared minus 1, then actually this Orlich norm is finite if and only if w is sub-Gaussian. So you have norms which kind of encode nice statistical properties of your random variable. If you change this Young function, you can also show that finiteness of the Young function is equivalent to the random variable being sub-exponential, for example. Okay. So we then assume that the Orlich norms of our Hilbert space-valued random variables admit some norm and some p such that their norm decays up to a constant like h to the p plus 1. This is exactly the same as what Conrad et al. Did, except that we kind of allow for more variability in what statistical models we put on our noise. Right? It can be sub-exponential, and our choice of norm fits well with that model. So under all of these assumptions, if the initial condition of our initial value problem belongs to this dense subset where we can apply our numerical method, we then actually have a stronger norm. We're taking, so let's go from inside to outside. The inside is, it says, what's the worst case over any random realization of my trajectory? What's the worst case error of that single function? This is a random quantity because I'm just looking at an arbitrary random realization of my trajectory. I then integrate with respect to this Orlich norm. So a rule of thumb, if you have a supremum inside an expectation, that quantity is going to bound something where the supremum is outside. And this quantity now decreases in the same way that we saw for the Conrad et al. Paper. Again, you have a balance between the order of a numerical method and the order, so to speak, of your randomization. Because you don't want to randomize with variables that decay to 0 too quickly, because you will not capture enough of the error. You'll be overconfident maybe. But if you decrease too slowly, then you're going to obscure some things and you'll lose on convergence. So let's just compare these convergence results. Conrad et al. Have a uniform local truncation error that's valid under strong assumptions on the vector field. And this recent work it places less strong assumptions on the numerical method. And this is important because typically PDEs, time integration for PDEs is really much harder than the finite dimensional case. Okay, I'll end with some insight which I like, and I admit it's quite ugly if you don't have your head stuck into error analysis of numerical methods. And it's the importance of error decompositions. So something that's common to both the work of Conrad et al. And this work is this bound, essentially. We want to bound at a single time step the error between our true solution and the random approximate solution, and we can bound it basically using this. So it comes from just how we define these quantities. Now, Conrad et al. Did the following thing. How do you control this? Right? You do the usual trick. You add 0 and you apply the triangle inequality. And the 0 that they added was depending on the true flow map. Because of this choice of error decomposition, they used the global Lipschitz property of the flow map to control the first term, and they used uniform local truncation error to control the second term. What we did was we added a different 0 simply. We added the 0 which was based on the deterministic numerical method. And this enabled us to use a non-uniform local truncation error assumption for this term, and a global Lipschitz property of the deterministic numerical method for the second term. And if there's anything that I'd like you to take away from this talk is that if you want to do error analysis, it's like a game, right? You have to know for what application you're working in, what assumptions are reasonable and what assumptions are probably too strong. And these assumptions tell you they'll guide you to basically choosing the right error decomposition. So in our setting, it's okay to have strong assumptions on the numerical method, but it's not okay to have strong assumptions on the flow map. So that's why this assumption was much better for looking at ODEs and Hilbert spaces. So what? So what's the point of all of this? Just to recap, what Conrad et al. Did 7 years ago, actually it's more than 7 years ago because they had to struggle, I was told, to get it published. It was a Herculean effort. They looked at finite dimensional ODEs. They assumed uniform local truncation error, which I would like to emphasize is quite strong. I mean, there are lots of ODEs for which it doesn't hold. And they assumed a randomization that decayed slower than ours, and they obtained an error in L2, right? What we did is that we looked at operator differential equations on Gelfand triples. If you don't know what that means, it doesn't matter. It's just kind of a way of looking at PDEs as ODEs on Hilbert spaces, roughly speaking. We don't assume uniform local truncation, which is really important for PDEs, I would say. The cost of this is that our randomization decays slightly faster. But the benefit of that is that we get an error that's stronger in some sense, because it's not necessarily just L2. It can be a sub-Gaussian error. If your randomization is sub-Gaussian, this error bound tells you that worst case error over any trajectory that you sample will also decay like a sub-Gaussian. It will be sub-Gaussian and it will decay like h to the min p and q. So the point of this is that randomized time integration is not just a finite dimensional concept. It works in infinite dimensions as well, at least in Hilbert space settings. And it can work under weaker assumptions than were initially assumed. And again, if there's one thing that you take away from this is that if you're interested in doing error analysis, it's like a game. Where can you put a lot of the effort? The stronger, if your application supports stronger conditions, then tailor your error analysis to take advantage of that. All right, and I'll close with a summary. We started with inverse problems. I showed you that, we started from looking at overconfidence. We could then bound mean square Hellinger distance in terms of kind of a double expectation of a forward model. We then bound this double expectation of the forward model using randomized, basically doing error analysis for randomized time integration. So one thing which I haven't really addressed, and this error analysis doesn't tell you how to do, is how do you choose a good randomization? The error bound, as you might have seen, all of the constants were swept under the carpet. And typically these constants will make a difference, right? The error bounds only matter when you're letting h go to 0, but typically we can't let h go to 0. So the constants do matter. And yeah, it would be really interesting to see, depending on what problem you have, how do you choose a good randomization? So with that, thank you for attention.
Thank you, Han. It's really interesting, the comments from numerical analysts. Why would you take a perfectly good deterministic method and mess it up by adding randomness, in light of Philip's comments on Monday, which, if I can paraphrase, were, why would you take a perfectly good probabilistic method and mess it up by throwing away probability distribution? So this community has a bit of a different perspective now. It'd be interesting to hear those two groups, Philip and the numerical analysts, talk to each other.
Yeah. Yeah.
Are there any questions for Han? Yeah.
Thanks. Very interesting talk.
Thanks.
I have two questions, but one is that basically, so your contribution is to relax a very strong assumption made in previous work. Like you say.
Yeah.
Do you have like kind of examples of like PDEs which are covered by like, your
Right.
assumption?
Very good question. So heat equation, for example. The heat equation would be covered. I mean, I must admit, I don't do numerical methods for time-dependent PDEs. It's kind of like what Chris said. I mean, sometimes in PN, we're interested in taking a method that exists, introducing probabilities, PN ideas into it, and then using that. Because when I opened a time-dependent integration PDE book, it's really quite heavy. I don't want to get into that. I don't have time to do another PhD. I just want to take a method that works, randomize it, and you can use it. But these assumptions, they are satisfied for like typical PDEs that one would like to work with. For example, parabolic or elliptic. Of course, not everything, but for a large class, it is satisfied. We took, as mentioned, so this assumption here, we didn't come up with it ourselves. We took it from a book on numerical integration for time-dependent PDEs. I would never think to come up with something like this. But it does matter because if you can think of D as like if you have a Hilbert space of Sobolev space, for example, you can think of D as like a space of initial conditions which are sufficiently smooth. They must be a bit smoother than your ambient space. And this smoothness typically allows you to apply the differential operators in your PDE, for example. Yeah.
I think there was a question from Fisher. That one.
Yeah, so my question is like actually not really relevant to the main topic.
Right.
When you say like this applies to the different hypos, do you mean like you can treat like distributional like differential equations like basically like when you consider the line as some kind of distribution on like some B.
And okay.
I mean, I just wonder why like, you want to extend that to like a really generous.
So the machinery of Gelfand triples, which again I must admit, that's not my bread and butter. That's typically one setting in which people formulate time-dependent PDEs as ODEs and Hilbert spaces. That's like the machinery in which, for example, you can even make sense of a PDE. They typically apply they take a PDE and they transform it to a weak form. And having a Gelfand triple structure allows you to do this to some extent. Yes. But more than that, I cannot say. I'm not sure if, sometimes there might be some distributions, but I cannot be sure.
Yeah, quick follow-up. So the heat equation is a setting where you don't have uniform local error. Is that a counterexample to why that will be a strong assumption in the previous work?
The uniform, okay, so for the uniform local truncation error, that's an assumption on the integrator, on the deterministic numerical method. So do I understand your question correctly?
I think so, yeah.
Yeah, so I mean,
So I guess what I'm wondering is if you pick like a typical integrator for the heat equation, right?
for example, implicit Euler.
Yeah.
This works. Yeah.
Meaning there you would have non-uniform local error, so you need your result and doesn't suffice to rely on the work from 2017.
I'm not sure, I'd have to check. Yeah, sorry, I don't have it off the top of my head. But it's a good question. Right. Thank you.
Maybe Chris has.
Thanks. Yeah, it's really interesting.
Thanks.
The challenge that you mentioned at the end was how much noise to add.
Right.
You know sort of that's what you want to do, but in terms of broad scale.
Yeah.
And that seems like a hard problem, but if you're in an inverse problems context, then you have to potentially consider sort of a parametric distribution of noise and then jointly estimate those parameters along with all the parameters in the Gordon model and so on. I was wondering, has anyone tried that and do we know if that works?
I don't know if anyone's tried that. I know people who would be really interested in how do you choose your randomization. I'm not aware of someone who's done that, but yeah. But thanks for the question. It's certainly a natural thing. I mean, as mentioned, this analysis doesn't tell you what distribution to choose for the randomization. And I imagine that would matter a lot.
Yeah.
One more question.
Sure.
Right, so you consider like discretization with respect to times.
Yes.
So then, which time you have function and then have to update and
Yes.
practice, so this for each time point, so this function is also discretized, right? If you consider PD through one, right? Then, like in principle, you should also randomize this like spatial direction, and also like and any like plan to like extend your result to that kind of distribution.
No, but it sounds like we could do it. Maybe we should investigate that. I mean, that's a great question. I don't know if that's been done yet. And to be honest, we didn't implement any numerical experiments for this. This is purely mathematical. Yeah. Thanks for the question.
If I could ask one more question.
Definitely.
I think, so if I've understood correctly, everywhere you kind of assume that you have a fixed time step, right? H. Is that correct? I saw some HK.
Right. For our setting, so Conrad et al. Assume a uniform time grid. We don't.
Okay.
We can have different time steps. So this is the setting in which we work in the 2022.
I see. Okay.
Right.
And so in the context of an adaptive time stepping method, where it's really deciding how large of a step to take, like dynamically within the solver routine, would like does it basically is it a sort of implicit assumption that this time grid has to be specified a priori and independent of the solver, or?
I don't think so.
Okay. Cool.
I don't think so. No. It's convenient for the error analysis, but I don't think anything stops you from saying how far ahead should I go. But that's definitely something we didn't look at all. Yeah.
It seems Philip may have.
Yeah, sure. So you looked at local truncation errors.
Yes.
To sort of match the deterministic solver. But I'm wondering what happens with other properties of the solver, such as stability and so on.
We didn't look at that. Yeah. But I imagine if you take these methods and you randomize them, I wouldn't expect to preserve things like stability. Because you take the output of a numerical method and then you randomize on top of it.
Methods that are already sort of A-stable will remain A-stable?
I don't know.
I would guess, but explicit solvers, I would be very scared.
Sure. Yeah, and this is why using something like explicit Euler is probably not a good idea.
Yeah.
Yeah. But I think even in general for a lot of time-dependent PDs, people avoid using explicit solvers anyway.
Yeah.
Thanks for the question.
Okay, let's thank Cal again.